Hi all, my name is Digger the Badger. Thank you for joining us in this session. You will be learning about the Navajo Nation Abandoned Mine Lands Reclamation UMTrika program. Thank you.
Hello, my name is Melvin. Today I'm going to give you a wide overview of some of the sciences that are involved with our program. We are dealing with what's called abandoned mine lands, sites that have been abandoned on the Navajo Nation, and we also have a cooperative agreement with the Department of Energy on what's called the uranium mill tailings sites. So the main purpose of the abandoned mine lands is to ensure the protection of the public health, safety, and property of abandoned coal and non-coal mines. And we also are looking at lands and waters that have been impacted by the mines in terms of environmental conditions. When we are looking at the different type of sciences on the Navajo Nation and talking about abandoned mines and the UMTrika sites, we're looking at both surface and underground mines. When we're looking at these mines, there's numerous dangers that are associated with them. We can have physical dangers such as your dangerous high walls, and we also have underground mines where we have unknown conditions. We're not allowed to enter any of these mines, so what's on the interior, we don't know. There's physical dangers such as unstable high walls and roofs, but there could also be wildlife that are using these underground mines as habitat. There is also a legacy of mining to the people and the environment. When we're looking at abandoned uranium mines, there have been people that have been impacted from cancer to families that have lost their loved ones. So when we do our initial public relations, we have to understand some of the background in terms of the impacts of these mines. Mining is basically defined as the extraction of some type of mineral or ore that is of beneficial or economic use to the people. When we're looking at specifically the Navajo Nation, we're looking at coal, uranium, copper, sand and gravel, limestone. Even rock, just a basic rock is a type of gravel that we can be looking at as something that has to be mined. So when we're looking at our program, we're involved with both reclamation and remediation. Reclamation is looking at the restoration of lands to a more beneficial use, whereas if we were looking at remediation, which the UMTrika sites have done, they're looking at cleaning up a pollutant or contaminant, and this can be either your surface or underground features that they're trying to clean up. So I mentioned mining is the extraction of minerals. When you're looking at geology, we're looking at different type of ore-bearing units. And then we also have hydrology, which is water, and water can be both underground and surface. And we also have different type of engineering, like civil engineer, who are looking at structures, but they're also looking at different kind of landforms. Mechanical engineering, which is looking at mechanical movements, which can get into some of the heavy equipment that we utilize on sites. One of the bigger things that we utilize in terms of documentation is called the Geographic Information Systems, GIS, and we'll be getting into that in more detail later on, but we're looking at how do we document for historical purposes a point, line, or polygon. One of the big things we have to do before we do any type of earth movement on our reclamation or remediation, we have to be in compliance with what's called the National Environmental Policy Act, and this is looking at your environmental considerations like your biological surveys, archaeological surveys, your Clean Water Act, but also community participation and how we are keeping them informed about some of the activities that we expect to do. If you were to look at this hydrologic system, we're looking at stuff that are being dynamic. Things are always moving, and we're trying to emphasize to students that there's different subjects, different disciplines that you can get involved with. We also want to stress to you guys that there's different kind of partners that you can be developing. You're looking at networking, where you're able to meet professionals, and this will lead you to eventually finding role models out there that you can be in contact once you go into college, and any of these conferences would be your mechanism to get into contact with them.
Hello, my name is Gilbert Daisy. I'm one of the civil engineers that do abandoned mine land reclamation all the way from the beginning to the end. So there's a process that I go through, and that's what I'll be trying to demonstrate to you. Some of the content of this presentation is going to include what is an abandoned mine and how do we rank them. And then after we rank them, how do we prioritize them, which is what ranking is. And then how do we eliminate those dangerous features. Finally, after I show you how we do it, then I can show you the exact, the methods that we use, that we implement, what we use from science. What do we have to consider? The biology, the archaeology, Clean Water Act, and then the people itself. So what is an abandoned mine? Well, an abandoned mine can be, it's wherever there was mineral of some sort, in this case coal, was extracted from the subsurface, from underground, and then used and transported somewhere else. Up till 1977, there wasn't a law that said you have to reclaim the land that you just mined at. And it still doesn't exist. So for the hard rock mine, like uranium mining or gold mining, you can do your mining and then you can just leave it behind. So that's an issue. The abandoned mines will have pits, will have high walls. High wall is like 100 feet high wall that's unstable. A pit is if you walk into that pit, it's not going to be easy for you to come back out. Or there might be an underground mine working that's going horizontally where the coal seam was at. Or you might be getting to that coal seam and you would use an incline to get there. And then there's other things that are associated with that. The features, they're not always stable. So there's subsidence problems that exist. So if you're walking and everything looks fine, and you step on an area where there's not enough pressure on the earth, it can subside and you can fall into a mine working. So it is very dangerous. An example of one of these subsidences was in the Namld. We had an abandoned mine that had subsided in 2 areas. So how do we eliminate these dangerous mine features? In our jurisdiction on the Navajo Trust land, just going out and finding abandoned mine features is not science-free. There's a lot of GPS work that you got to understand, GIS work, some databases that you got to look at. You got to look at the geology of the land. So you got to have a map that shows where the coal outcrops are at, so you know where to look for an abandoned mine feature. Map reading. You'll have old quad maps that you have to read, that you have to learn how to count, and learn how to get the distances on it. And directions. You got to have a compass. So there's a lot of just looking for a mine feature requires some science and some technology, and you got to calculate your angles. So you're going to have to do math. You got to know about geology. You got to know about engineering. After we get all these abandoned mine features, what we do is we determine which ones are most dangerous to the least dangerous. So if there was a community, like let's say Namld had a community of about maybe 2,000 people. Their dangerous mine feature is immediately right there, right across the road from the community. That would be considered a priority one. And it would be a mine site that you would take care of immediately because it's right next to the community. It's impacting the infrastructure at the community. So you're doing engineering work on this site, trying to determine how to do this, how to eliminate this dangerous mine feature. You also have to understand the environment on the other hand. So you got to balance those two out. So if you're doing engineering work and you're doing conceptual designs and you're already impacting the environment, which includes all the animals, all the birds, all the fish, the soils, the people, if you're already offset, then most likely when you take it to the community, most likely when you take your NEPA document to your funding agency, you won't be able to get the work done. So that's why you got to be consistent at the beginning, that you balance both the design side and both the environmental side. Each government has its own procurement process. For the Navajo Nation, government has its own procurement process. It's got a Navajo business regulatory regulations that you got to follow. So you got to go through the procurement process, which can take anywhere from 1 month to 6 months, and I've seen it go for a year. So it takes a while for your contractor to get approved so that he can work. I've had a contractor that looked like everything was good to go until up to the point when they showed up at DOJ we were told that they were suspended from Navajo Nation work. So it can be a lot of complicated stuff within the Navajo Nation government. So these abandoned mine sites, they have old buildings, old mining equipment, and then they're out in areas where it's royal. There's hardly anybody that goes out there. And you can find artifacts. It could be a set of bow and arrows. It could be a pottery. So those are all historical properties that you have to consider so you don't damage them. That's archaeological and historical compliance. The next thing you got to comply with when you're out there thinking about the environment, you got to think about the compliance with the Clean Water Act, Section 401, 402, 404. 401, 404, you got to implement that into your NEPA document. You got to show that you're not going to have a release of sediments or release of any kind of contaminants into the waters of the United States. So in order to do that, you got to talk to the Army Corps of Engineers, you got to talk to the Navajo Nation EPA Clean Water Section, and you got to prove to them that your project site will be stable during construction and after construction. During construction is where the 402 section comes in, where you're ensuring that you're not transporting any sediments. So there's examples I'm showing you. One site has 2 ponds sitting there. So the first pond, what it's doing is collecting sediments. It's collecting sediments where it doesn't allow any sediments to leave, and it's also backfilling a farmer pit area. The first dam is using sediments that's being blown in and that's being washed in, and it's backfilling an old pit. And then the dam that's down gradient of it, the sediment retention system that's down gradient of it, that controls all the flow that's coming off the mine itself. So it's a 401 and 404 in compliance. So when you're out there, when you do your value engineer, let's say there was the principal engineering tech, myself, and the GIS person. We went out there to look at a mine site, and we wanted to see how it can be reclaimed. Each one of us would do a conceptual design, conceptual drawing. And then we would all get back to the office, and we would sit down, and we would talk about how the reclamation can be done. And then when we come to an agreement, we do a conceptual design, which is not a whole design, it's just conceptual. You just, you know where you're going. But you're thinking, this is what we're gonna do, but this is not 100%. So after that, you will move on to designing the whole product itself. So you do the whole product, and there you have the design and the cost estimate. So the design and the cost estimate is very important. That's how you're going to sell your product to the contractor so he can do the work. Now you do an as-built. The work like this involves surveying with RTK. You got to have GPS units. You got your data collection system that you got to use in order to make your final product. That's the same for the initial, what was on site before the reclamation, and then after the reclamation, what way you got done. So there's math, science, and STEM's involved again. The other thing to be conscious of is the fact that you want to build your reclamation project to where it will work with nature. I was telling you earlier that structure, the first dam that I was talking about, is actually allowing sediments to refill a pit. Now the system is working to where what Mother Nature wants to do, it's working with it. The other thing is this picture that I got with big retaining wall. Mother Earth, if you look around, look at these hills, there's always an escarpment, and then there's a concave slope, and then a slope that's almost flat. So that's how you want to design something so that you can work with it. So those kind of concepts are called geomorphic concepts. You use softwares that are capable of doing natural regrade. So there's a lot to learn. The regular reclamation, just backfilling a hole, is a lot different from developing a structure that will be standing there for a long time, for decades, maybe even 100 years if you can design it that well. So now, if you have any questions, please respond.
Hello, my name is Joni Talbot, and I'm the Senior Environmental Specialist, aka the Physicist. And I'm going to take you through what we refer to as UMTrika. So the primary goal of the UMTrika efforts are to do remediation of groundwater cleanup, and we'll get more into that. But first, let's go a little bit back into history and explain how did the water get contaminated in the first place. So you heard from our engineers about reclamation work of abandoned mines, whether it was coal or uranium. Now, back in the 50s and 60s, you don't just take rock and use it like that. You have to go through a whole process in order to get that uranium or to get that material that is of interest out from that naturally occurring material, or the uranium ore in the mining case. Back in the 50s and 60s, there were companies that, not just on Navajo Nation, but across the whole US, processed this uranium ore in order to get out a product that most people refer to as yellow cake. During this processing, it is a lengthy process, but back in the 50s and 60s, there weren't any forcible regulations that required these companies that went out and processed in these areas to regulate how exactly they would remediate or clean up the work that they were doing for these different sites. On Navajo Nation, there are 4 sites where they processed uranium ore. That was Shiprock, New Mexico, Tuba City, Arizona, Monument Valley, Arizona, and Mexican Hat, Utah. At these sites, the types of material that were left behind from the processing that was done by these companies were things like mill-associated buildings. They were actual mill tailings, which is the dangerous part of the hazardous waste that was left behind. Any type of windblown material is also contaminated material. So through the weathering process, some of this material that was not stabilized was able to erode with the wind and with any type of water, and it was able to percolate as well into the groundwater. So there is a plethora of issues that came from these companies processing uranium ore at these sites, and yet they didn't do it in a way that was environmentally sustainable. Now let's talk about the solution and how people thought they would address that. 1978, UMTrika is passed by US Congress, Uranium Mill Tailings Radiation Control Act. And the main problem that was of concern during that time was radiation as well as radon gas emissions. Uranium is a very big molecule, as well as thorium, and they are prone to radioactive decay. In the process of radioactive decay, radon gas can actually come as one of the daughter products as uranium from uranium and thorium radioactive decay. And so radon gas is a hazard for people to inhale, and of course radiation is a hazard if you are nearby a source or you're being constantly exposed to it. So those are the different types of hazards that they saw back in 1978, and they gave the responsibility to Department of Energy to go in and do what we call surface remediation. So remediating the surface of the ground. As I mentioned earlier, the problem was that there were mill tailings and hazardous waste that were basically, it was just stored as a pile, and there was nothing to keep the wind from eroding it off. So there was wind-blown sediment. Some of that material was damp or sludge, like a sludge, so it percolated much like a coffee, right? So much like coffee, some of that contaminants of concern actually percolated into the groundwater. So now we talked about surface contamination. That windblown sediment, those materials that were just sitting out in the open, DOE had to create some engineering designs to talk about how they would basically stabilize in place. So they go through a very lengthy process to do assessments on where the contamination is and looking at some of the basic geology in order to figure out what was the best location for them to stabilize in place. They also had to license what we're going to refer to as disposal cells. Those disposal cells have very specific requirements in their engineering. After all of that assessment and figuring out, okay, what exactly are the site characteristics, whether they're physical or chemical, geological, and based off of that, they come up with something called a site observational work plan that pretty much sets the tone for how groundwater compliance strategies will be put into place. It also shows a way for the surface remediation to be completed. Here you see a 3D model of the site itself after surface remediation has been completed. So all of the hazardous waste and hazardous materials have been encapsulated into an engineered cell that in a sense isolates all of the material, and it addresses any type of radon emissions with this 76-inch thick low permeability radon barrier, which is basically just over 6 feet of compacted clay material, which keeps any radon emissions from coming out of any of the materials that are encapsulated, and also acts as a barrier between any precipitation, rain or snow, that could possibly dampen the material and create a source of percolation as well. On top of that radon barrier, we also have 6-inch thick of bedding layer, which helps to keep the larger rocks that are the stabilizing, the riprap material, from sinking into the radon barrier level. So it acts as a barrier between the barriers. And then on top, you have the riprap material, which is about 12 inches of very large rocks that basically keep any of the material from weathering and eroding. As I mentioned earlier, some of that mill tailings, when it wasn't encapsulated in an engineered disposal cell, was damp, and of course that means that due to gravity, some of that contaminated material, contaminant of concerns, got into the groundwater. So now we have contaminated groundwater, and how do we fix that? So US EPA was given the direction and authority to come up with standards in order to address these contaminants of concerns. Now DOE goes through a process of figuring out, okay, how exactly are we going to address each of these sites and get the standards down to what is acceptable by US EPA standards. Every single site is different. As I mentioned earlier, there are 4 sites on Navajo Nation. Every site has different geology. It has different factors that either help or are a challenge at the sites in order to address the groundwater contamination. For the 4 different sites, Mexican Hat, there are no remediation activities. Shiprock and Tuba City, there's active remediation. And at Monument Valley, there's what is called natural attenuation. So as you can see, there are different types of groundwater remediation that you can do, from no remediation, which is very obviously low maintenance to just monitoring, all the way to active remediation, where you're doing a lot more. Shiprock and Tuba City, there is a pump and evaporate. So they'll pump out contaminated groundwater and that evaporates, but they would have the material, whatever's left, and that would all be encapsulated, transported to another disposal cell in Colorado. And Monument Valley is natural attenuation, which uses plants, phytoremediation, a very fancy way to say that plants would basically uptake the contaminant of concern, which for Monument Valley is nitrogen, compared to when you look at Shiprock and Tuba City, the main contaminant of concern would be not just nitrogen, nitrates, it would also be uranium and also sulfates. As we look back and say, how effective was this treatment of groundwater, we can move forward and say if it was effective or if it was not effective. And if it was not effective, there are alternatives to have other systems of remediation in place, which includes things like uranium sequestration, as you can see an example of a picture of a pilot study here, electrocoagulation, reverse osmosis, and other different types of alternative remediations. As you can see here is a wave unit, which uses basically the wind in order to increase the efficiency of evaporation.
Hello, my name is Victor Lee. I'll be talking about GIS today. What is GIS? Well, GIS stands for Geographic Information Systems, a powerful solution using hardware, software, and gathering a lot of data. With all that, we can explore a site, in our case, a mine site, geographically. Location is important to people and business. From this, we can gather, view, understand, analyze, and interpret information on a map. All this information will have layers of data that we can see patterns and relationships. From this, we can display trends or complete data in a simple way to make a better decision. Additionally, GIS gives us a clear understanding of what happened, what is happening, what will happen in a geographic space, in our case, past mine site. You will find GIS in all technologies such as weather map, medical field, emergency, and of course in your phones and vehicles. GIS brings geographic knowledge in which we utilize for our reclamation site to make better cost-effective decisions to continue our reclamation work. We determine the best way to approach a past reclaimed site using location. With this, GIS allows us to gather data, design, engineer, and make and create a safe environment for the people and the community. Consider a mine site. We gather data, understand the data, analyze the data, using map and engineer a solution for the reclamation site. STEM, science, technology, engineering, and mathematics. Why is it important? It harnesses and creates a higher learning from skills from the classroom learning to the real world. It emphasizes communication, research, problem solving, critical thinking, and creativity to make our lives better. Stuff that student needs in today's work regardless of interest or career goals. It's the key to innovation and creative problem solving. Technology makes our lives better. It implements change, minimizes error for all of us, working as a team for a greater impact than working alone. And lastly, it's not just only for science and engineers, it's for everyone.